then a rapid handling of all the other things we learned. Regression. The regression, we have it in two versions. We talk about the simple regression. The simple regression is where we put in a line and some scatter points like that, right? We showed how we calculated the line by the least square idea. We minimize the square distances. That's why it's called the least square method. And then the whole thing is about the statistics around it, because many of you would have seen that we could put in a line and some data points already long before you show up in this course. But what you may not have seen so much is how to talk about and how to quantify uncertainties in such a context. That's maybe the new thing in this course compared to what you've seen previously. There is a way to quantify the uncertainty about the intercept and the slope, right? We should think about the next time I collect the data, I get a different result. It's the same statistical challenge. It's like computing a mean. But now it's not just the mean. Actually, the intercept is almost the mean. But it's a mean and a slope. But the slope also expresses the mean behavior in a way, right? So it's like computing a mean. We need to think about uncertainty. And someone found the sampling distributions for us. These sampling distributions are t-distributions again. So we can do statistics on those means, on the slopes and intercepts by the t-distribution, and you got the formulas for that in the notes, so you can do that. So we can do, whenever we have that in place, we can do hypothesis testing or confidence intervals. We could take that and put it into confidence interval for the line, or prediction interval for the line, which is typically a wider thing. These were the two intervals for the line. Depends on how we use the line. I mean, do we use it to estimate the average? We have the weight-height example. Do we use the line to estimate the average population weight for people of 180 centimeters, right? All the people, the subpopulation that are 180 centimeters. What is the mean weight of all of those out there in the population? If I use the line like that, it's the confidence interval. That's the relevant. If I use the line to predict a single person's weight, that's why we call it prediction. The line value is the same. There's only one line here. But if I use it to predict a single person, it's a different uncertainty. I have the individual variability on top of it. So it's more imprecise. When you use regressions as a quality control in a production line, for instance at Lundbeck, it's a prediction thing you're doing. You predict the content of individual tablets. You run it through, for instance, an NIR machine. You put some light on it. You make a regression model. You predict the amount of active substance in the tablet. So you predict on this individual tablet level. So if you want to know about uncertainty, it's the prediction interval you should use in that context. You're not estimating the average level of all your tablets in that case. That could be interesting also, but when you use it as an online quality control thing, you predict the individual tablet. So that's prediction. It's important sometimes. We could quantify. Actually, there is a relation between this correlation coefficient that we started out with and the regression setting. It can be expressed in various ways. Positive correlation, positive slope, negative correlation, negative slope, right? Correlations can only be between -1 and 1. Slopes are on the original scales of x and y. If we square the correlation, it has a specific interpretation, funny enough, but it's there. If we square the correlation and see it as a percentage, because that will be a number between 0 and 1, right? If I square the -1 to 1 number, it becomes a number between 0 and 1. It has a nice interpretation, namely the proportion of the y differences or y variability, which is explained by x. For instance, if everything is explained by x exactly on the line, never happens in real life, but if it was exactly on the line, the correlation coefficient would be 1, so 100% of what goes on in y is explained by x. If there's a large variability, not so much, right? Nice interpretation. Then we took it on to multiple regression. This is also challenging, but you have to know about that. It's an important tool. What if there are more than one x? Well, as a first go, it's straightforward to express this. Should be a plus here, plus epsilon I. We can just add in all of them in this linear additive expression to have a multi-dimensional function in a way, a function of many x's. So in this case, it's like a plane, right, in the 3D space. So y depends on both of them, and it's a linear. So it's not a curved plane or anything. It's a strict linear plane, right? So we can just do all the same things. We don't give you now all the formulas exactly, because now it becomes slightly more technical. We would need some matrix stuff, and it's an optional thing. It's not syllabus for you. So this is where we have the chapter where many of the things, we just tell you how to extract it from R. We don't give you all the hand calculation formulas for everything here in the multiple linear regression setting. The understanding and thinking is very much like the ordinary regression. All the residual investigation part is exactly the same business. We can do intervals, confidence intervals, prediction intervals, and still the R squared express the proportion of Y variability explained now by the x's we have. It's important interpretational-wise to think about what is the interpretation of a multiple linear regression. It is the effect of one x having corrected for the other one. So it's kind of a keeping the other one fixed interpretation, right? So beta 1 expresses the relation between x1 and y for the same values of x2, right? And that can influence the interpretation. It's very good. I mean, it's what we should aim at. It can also be challenging if the x's are correlated to each other, because then there might not be much information about this unique effect, but nevertheless. That was simple and multiple regression, very much used tool out there. Other used tools are the next two ones, the one- and two-way analysis variances, that generalizes these one- and two-sample situations that we started out with to multi-group comparisons. And of course, real life consists of many multi-group situations, not only of one- and two-sample situations, right? So that's an important tool to have in the toolbox also. For instance, the first one, the one we called one-way analysis of variance, that's the generalization of the two independent samples case, because this is where we consider that we have k independent groups. And usually independence means that it's, for instance, different people or different animals or different whatever units in the different groups. Then we learned that we could make this an over table where we have the source, the sums of squares, the mean square, the f, and the p-value. And sometimes we also see the degrees of freedom in this table. It's spit out to us by R, as it would be by any software out there. We focus on the p-value first. That tells us whether we could actually distinguish between and within. That's also a way to talk about it. The between group, the between treatment variability, and the within treatment, within group variability. We get a p-value that links the between variability, that measures whether the groups are more different than you would expect by chance. That's what this p-value expresses to us. So it's the hypothesis test that the groups are the same. Of course, they are not when you observe them. The only thing you have to decide, are they more different, those means? Because the analysis of variance, please remember, is about the means of the groups. Right? We compare the means of the groups just like the two-sample setting. We are comparing the two means. Now in the k-sample setting, we compare the k means. By computing certain variabilities. That's why it's called, funny enough, analysis of variance. We discussed that. The p-value here expresses, if it's small, we have proved that the treatments are different. So that's often the first place we look in an analysis of variance. Then we could also do post hoc comparisons of the original pairwise groups, for instance, a bit t-test-like. And it looks very much like a classical t-test when we start doing the post hoc, but we should remember that it's not exactly the same, because we use in the post hoc comparison of groups, although it is a t-test and it looks like the original t-test, we are using variability information from all the groups, which makes the degrees of freedom a little different, and the variance estimate we use is also one we take from the ANOVA. Sometimes it's pre-planned comparisons, and we just do them with an alpha level of 5%. At other times, we may just go along and do all the comparisons that we can do, but then we should be careful and not be overly optimistic. And the recommendation here is use the so-called Bonferroni correction. So if I do 10 comparisons, I would not use the 5% level in each individual comparison. I would use the 0.5%, that is 5% divided by the 10, right? That is our way to be cautious here and not to do selection bias mistakes or significance by chance mistakes that we could otherwise risk doing. All of this generalizes almost straightforwardly to the case where it's not only a single-way table, but it's a two-way table. So the samples are no longer independent. It could be the same persons in the different groups. So they are linked on the other way of the table. So there is two ways of the table. We can generalize, we compute means, and the one way means, and the other way we could quantify how different are these means, how different are these means, and we put that into the ANOVA table. How different are the treatment means, how different are the block means, and then we get the similar f-tests and p-value, and we could also do the similar post hoc. Remember that the post hoc for the two-way, you need to read the sentence in the note that says you don't find a method box explicitly for post hoc in the two-way. You are referred to the method boxes of the one-way chapter. That's an important note to realize, because otherwise you think there is no post hoc thing for you to be doing in the two-way table. Two-way and over, yes there is, you just have to look back, right? It's an important little detail, not to get confused about what you could do. Finally, last week, we finalized by looking again at now proportions, categorical data, count data. So a bit different type of data, but I hope you get the feeling also very important. Like when we do polls, what's the percentage of who votes yes and no for our Thursday election or referendum? Please remember my formula for the confidence interval for a proportion that will help you in life, right? Do you remember? Well, go check. P hat, 1 minus P hat over n, and the root. That's the statistical uncertainty of a proportion P, of a percentage P. That's a good formula to know by heart. So that means you can immediately evaluate the value of a percentage when it's given to you. If you know n at least, you should of course ask, someone gives you a percentage, you should ask, if they don't tell you, hey, what's the n? Is it 10 or is it a million? We can do normal-based confidence intervals and hypothesis testings for 1 and 2 proportions. Normal-based, set-based. We have some set tests and some normal-based confidence intervals. Then we also saw that for 2 proportions and multiple proportions, we had, for the 2 proportions case, we have 2 options actually. Because if there are more than 2 proportions, we saw the percentage of malformations from Sundhedsstyrelsen in babies in Denmark, where we had 12 proportions. It could also be multi-categorical, that not only malformation or not, but no malformation, severe malformation or just soft malformation. There could be more groups. So it could be an R by C table, row by column, with more. And then we had this chi-square test where we basically compare observed and expected values like this. Not giving you all the details here. That can test whether we have the same sort of distributions or proportion around across the different settings. That's the whole course in. I aimed at 45, it was 50 with the little challenge I had in the beginning. So I usually end this by asking, it's dangerous, but was this useful at all? Usually this is the answer still, so that's why I do it. Anyway, let's do the break, 15 minutes, and we'll be back here.